So, wir sind zeitlich ein bisschen später als geplant.
We're starting a little bit later than planned. However, we've also answered a few more questions than planned. I hope that you feel relaxed now after the coffee break, and this is why we would like to move on. Let's welcome Professor Dr. Lars Enghardt from DLR. He's a physicist, doctorate in oscillations and waves, and he's been working with DLR since 1997. He's the head of the Department Engine Acoustics at the Institute of Propulsion Technology, and at the same time, he's the head of the Institute for Electrified Aerospace Propulsion Systems and the spokesman for the Aircraft Noise Expert Committee, an interdisciplinary DLR group. In his presentation, he is going to present the next generation engines to us. He's going to talk about engine linings. And yesterday we have learned that this is so important for noise reduction. You are also going to talk about the positioning of the engines. We have learned that there are different options with pros and cons. Then you're going to talk about the boundary layers, and you're going to address electrification as well. And yesterday we talked about how to measure the noise produced by the individual components. So you are probably also going to elaborate on that. It's far more complicated than we assume. Good morning, ladies and gentlemen. This is my presentation. It's my pleasure to talk about propulsion systems of planes. And this is the title of my presentation, quite a long one, Current State of Development of Propulsion Systems from the Point of View of Aeroacoustics. And aeroacoustics are, of course, important when it comes to sound. Let me show you the same slide in English. I'm going to speak German, and you will get simultaneous translation, and thanks to the interpreters, by the way. Let me start with propulsion systems. I have to pour a little bit of water into the wine, as I'm not going to address every propulsion system. If I would do so, I would need 5 hours. But what I'm going to talk about is the lined engines. I will show you an overview, and in the second part of my presentation, I would like to focus on electrification and propeller propulsion. What is the motivation behind all that? Those who watch the development of engines have probably noticed that the engines are getting bigger and bigger. How comes? Well, the so-called bypass ratio, and we heard about that yesterday, is increasing. It's getting higher. And this means we have a lower fuel consumption and less noise at the same time. And we're still arguing, but in a positive way, what the optimal point is. In the past, people said bypass ratio 10 is the limit. Now it's 11 already. And yesterday we learned that 15 is being developed. It's being tested, and we assume that when it comes to the lined fans, even a bypass ratio of 16, 17 is possible. So here you can see the current generation and the next gen with a bypass ratio of 12 and hopefully one day 16. So this is the airflow passing the engine. And next gen, as I already mentioned, might have a bypass ratio of 16. Here you can see that the engines have changed in their design, in their size. This was also mentioned by several speakers. They're getting bigger, heavier. It's it's very difficult to assemble them. And why are they getting heavier? Well, they're designed in such a way that the nacelle is a little bit shorter and more compact, which means the length-diameter ratio will decrease as a consequence. And that's how we will get more compact engines. In the first part of my presentation, I'm going to focus on the following question. What kind of impact does such a new compact engine with a short nacelle have on fuel consumption? And what kind of impact will it have on noise? And what about the long-term benefits? And in the second part of my presentation, I would like to talk about electrification. I would like to talk about certain things which can be used to reduce noise, and I would like to talk about these smaller engines which might be an option for the future. Of course, I'm going to address the linings, which were also mentioned on several occasions yesterday. And here it is important to see, but I'm going to address that briefly. I don't have the time, that these kind of shorter nacelles are also quite susceptible to lateral wind. So if the wind does not come from the front, but laterally, you have to expect the engines producing more noise. And this is something you have to be prepared for. And then we also have to address the engine positioning. And how is it assembled? I mean, you have to integrate them to the fuselage. You have to make sure that the landing gear is not getting too big, and shielding needs to be guaranteed at the fuselage. This is something which is, of course, key when it comes to the design of future aircraft. Electrification is something which aims at replacing current technologies in order to reduce noise. Let me ask you, who believes that electrification might have a positive impact on noise? Hands up. Who believes that electrification of propulsion will have a positive impact? I see some of you are quite hesitant, not sure, but we will take a deeper dive into that to answer that question. And electrification, of course, will bring new design options along, and I'm going to talk about that in a minute. Let's talk about lining of engines. You can see they're getting more compact, and as a consequence, we need, of course, space for the lining. And this kind of lining is being used at propulsions, at engines, which brings the best benefit, which means we have the noise source at the engine, and before the noise leaves the engine, it's being shielded by these kind of linings. We have a dramatic reduction. And as soon as the lining gets smaller, shorter, you will have a problem, which means this kind of effect needs to be replaced by something else, and one option is developing better liners. And this is why a lot of research is being done in this respect. You can see this liner on the top right-hand corner, and maybe you will get the opportunity to take a closer look. You can see this kind of porous surface. This is here our test plane, and we've been using it here. And this small part, the small element, is the best possible instrument, the best possible device to reduce engine noise. And we still try to understand the physical mechanism behind all that. How does it work? And how comes that it works so well? And can we further roll it out? And the 3 scientists from the Technical University Darmstadt told us yesterday that there are only limited areas of use for these kind of acoustic liners, but we would like to have a broader application. You can see that these kind of liners are very flexible, and we can use them more often, not as loudspeakers, as you can see it here in the center, but having resonators, for example, in order to absorb the noise to a large extent. And I'm a fan of liners, and you should also be huge fans, as they reduce engine noise a lot. So this is why we have to invest many more thoughts into the development of new liners. And here, a few words about the positioning of engines. Here you can see an A230. The engines are mounted below the wings. This is typical, the usual way. But if they get bigger, you need to make sure that you have a certain distance to the runway, and before making the landing gear even higher, to have the distance guaranteed, and we know that landing gear is of course a source for noise, we can mount the engines in a different position. And on the right hand side you can see one example. On top of the wings, with that T structure, or embed the engines into the fuselage. So there are different options, you can see them here. Here we have the engines in the back. We can also move forward, and as far as the drag is concerned, it is also quite positive, and we can also see positive impact on noise. So we analyzed it, and we learned that the fan, which is rotating in the engine, is of course causing noise. We have different flow scenarios, as due to the other embedding, we have a slower speed in the engine. And this kind of flow leads to specific noise. We have more noise deflection, which means this kind of boundary layer ingestion, which is of course positive for certain aspects, might have a negative impact on noise. And this brings me to the exciting topic of electrification. We're still quite far away from a proper electrification. This is what we learned from the Bauhaus colleagues yesterday. However, there is a lot of research being done in order to save fuel and, of course, to reduce noise. And this is why lots of you are probably thinking of buying an electric car. And the same goes for planes. Let me invite you to take part in the following experiment. So let's assume it all works. We have this plane here, this aircraft with 4 engines. And we have a hybrid engine. You can see in the back the gas turbine integrated in the fuselage, driven by sustainable aviation fuels, and the generator generates electricity, and this electricity is now powering the engines mounted under the wings. So, assuming that the gas turbine is shielded very well, what kind of noise can we expect? Is it much quieter than the original, the ordinary plane? This brings me directly to the Active Noise certification points. You can see 1, 2, and 3. 1 is the approach point, 2 is the sideline point. So this is where the airplane drives at full thrust, and 3 is then the departure point. And for all 3 points, we analyzed the noise sources and the way they change. And the prerequisite is electrification. And here you can see once again the engine, which was also shown to us by the 3 TU Darmstadt representatives. You can see the noise sources, the fan, we have the compressor, the combustor, the turbine, and the jet. And if we electrify, what kind of components are no longer needed? Well, the compressor is no longer there. You do not have to condense the air to burn it later on. The combustor is gone, the turbine is gone, and the jet is also being dramatically reduced. What is in the center, what is dark, will no longer need it either. And this is the calculation method. We created a database and gathered all the data of the different components of an engine. On the left-hand side, you can see the conventional engine, different curves representing the 5 main noise sources: fan, compressor, combustor, turbine, engine. Then we took out the combustion, we reduced noise deflection, and then we learned, okay, it's not fair because the jet is also causing some thrust, and we have to compensate for that, which means no longer thrust from the jet needs to be compensated for. And how can that be done? We leave the fan, and the fan rotates a little quicker, which means more thrust to the fan, and this thrust loss was compensated for. We increased the RPM, and this is a high bypass engine, and 20% come from the jet, 80% come from the other source. We had to compensate for that. And as a result, we had this electrified engine highlighted in blue here. And now let's take a look at the results. Well, the results are not that significant. The differences are not that significant as we expected. Assuming the technology works well and we can simply exchange a conventional engine with an electrified one, then when it comes to the approach certification point on the left-hand side, we have 2 dBA values. This is the noise level. This is what we hear or what we measure on one point. And then you can see EPN dB. This is then the perceived noise, the effectively perceived noise in decibel. And you can see that in both options we have some differences, but not significant ones. When it comes to the approach measurement point, it's even louder, which means with the thrust compensation, we got a little bit louder when it comes to the electrified engine. In the takeoff sideline noise certification point, the electrified version is quieter, and the same goes for the takeoff and flyover noise certification point. But we're not talking about 10 dB. It's not that much. So the benefit is not that big. If we took 2 engines and electrify them and keeping all the other technical aspects apart, then it wouldn't lead to a dramatic noise reduction. The planes wouldn't be that much quieter. But what kind of benefits will electrification bring? Well, we can choose different configurations. And here you can see, for example, distributed propulsion. And this is a configuration which was used for an experiment, the ATR 42600, which means on every wing we have 3 additional engines, and we have a hybridization, which means the standard engines will remain, but they will used as generators and will power 3 additional turbines, which means you have 4 propellers on each and every wing. You can see them here. And if you make progress in this technology, making sure that the propellers and the way they are assembled can be controlled in such a way that they have exactly the same functioning, so how can that be used? You can see 2 results. On the left-hand side, we took the 4 propellers, and you can see the 4 dots on every side, which means this is a plane, if you stand in front of it, representing a specific configuration, and you can see that the different noise radiation patterns overlap. You have zones where it's getting really louder and then zones where it's getting quieter. On the left-hand side, you can see all the engines are used in synchrony, so at the same time, simultaneously, and at the right-hand side, they're used or operated randomly. And you can see that the noise radiation looks completely differently. As a consequence, we have learned that it's much more complicated, and of course you can profit from additional engines, but how to operate them is quite complicated, and how to get to these white zones where we have a low noise radiation is something which definitely needs more thought. So operating them is something which is further being researched. But this brings me already to the outlook, which is a longer one today. You might know that everybody's talking about the air taxis at the moment, and why am I mentioning them? The air taxis or the airport shuttles have one benefit. They look aerodynamical perfectly, and you will get all kind of concepts and architectures. So all kind of designs seem to be possible. If you take a look at them, it's fantastic, at least fantastic to me. And I'm somebody who loves the design of planes, and it's great to see that we have so many different architectures. And if we have so many architectures, we also have so many configurations, and so many different designs are being tested at the moment. And therefore, we're quite optimistic that one day we can profit from testing these designs when it comes to building big planes. So having these kind of different vehicle types might have a great benefit for bigger planes. We can measure, for example, the noise they are producing, and we have quieter ones, louder ones, and we can learn from them. And some of the designs, as I already said, might be passed on to the bigger ones. And we are, for example, testing smaller lined engines. This is why we started with a new test facility in Berlin, which is suited for fan stages of small aircraft. So we can do quite a lot of experiments here. Further options. What has been done already, what works well, and what might be beneficial for the noise radiation. Here you can see the van variable area nozzle to reduce engine noise, which means the pressure which operates on the fan can be changed in a variable manner. Why is that important? Especially when you're approaching, the engine is not operating on a designed level. I mean, the best performance is always given when flying high. But when approaching, the engine is not working in an optimal manner. And this is why we found out that increasing the actual velocity is reducing the incidence and is then leading to an aerodynamic unloading. And this is something which can be used for propellers, something what we have in the system. And by varying the nozzle, we can have, for example, a positive impact. So these are two options we have analyzed, and we can see a huge benefit which is possible. And here you can see the detailed information on the paper I'm quoting of. And you can see that there are configurations which are really good for the performance, but produce more noise, highlighted in green and red. But in some cases, it's only a gut feeling. We need to take a closer look at it. So it's a trade-off between fuel consumption and CO2 emissions. So how can we find a good compromise which leads to lower fuel consumption and less noise at the same time? Let me summarize that. When it comes to future ultra-high bypass ratio engines, what is happening? Well, they're getting more compact, and this is why the length-diameter ratio will be reduced as a consequence, which means less space for the wonderfully noise-reducing technologies we have with the lining, for example. And this is why we definitely need to improve that. The engine positioning is, of course, a very important topic. Where should I assemble them? And if I assemble them, I have to make sure that I profit from all kinds of technical parameters which are known to us. Embedding the engines is getting more likely to increase fan noise, so this is negative. But we have the variable area nozzle and the variable pitch control. This is something which can definitely have a positive impact on engine noise. When it comes to electrification, however, simply replacing the engine will not lead to a dramatic decrease of noise. Effects could be seen, but not significant ones. And noise sources which have the combustion as a technology are not the main sources of noise. The distributed propulsion systems have a great potential to reduce noise, and this potential can be seized if you do the right thing. And finally, I'd like to say that a lot more research efforts need to be made. So this is my conclusion. We can see lots of changes to the better when it comes to engines, but still we have to do more homework. We are monitoring the market very thoroughly. We're watching what is happening from the technical point of view, and we're also monitoring the air taxis to learn from them. And in the next years to come, we will see very, very exciting and interesting developments when it comes to electrification, for example, and other technologies. But of course, you simply cannot exchange these kind of systems and hope that everything will be quieter overnight. And having said that, I would like to thank you so much for your attention. Professor Enghardt, thank you so much for having mentioned so many interesting things we addressed already yesterday. It's complicated. A lot of research still needs to be done, but of course there's also room for improvement. And we will have the Q&A later on. We have already a few interesting questions for you, but we're going to take the questions after the next presentation.